can't remember. Oh, no? I mean, this is the problem.
I think it's online. I think it's oh, yes. I mean, yes.
No,
Yeah,
no, it's totally.
I agree. I actually do. Everything okay? I should be off like this all of that.
Maybe we can.
I mean, maybe this side is better to make light inside, not
The middle one.
I mean, from here.
Yes, I think yes.
Is it
Yes, yes, yes. It was
and Jorge is here.
where they went out yesterday.
But he was here. More or less. I didn't know that.
Hola.
Yes, I didn't know that. I know that you are with, I know that, but I thought that you were online conversation.
No. I think
Say no, but you.
yeah.
So when you do it. So you have a zone.
Yes. I studied Friday, Monday, following.
As well with your wife, no?
Yes. And I wrote a reflection. Yes. Why that is it?
Are you doing all the water?
Yes. Because there are factors and I have a little cake that was closed, then cast out. Yes. No.
I mean, I think you did not understand that we need to write the paper.
Yeah.
You have been in a long time, I've not seen one page. Please, work on that. Monsieur,
How are you?
very well. Today, I have to make two interventions during the break, during the coffee break.
Coffee break in the morning.
In the morning and another one later, during the lunch break. And they are a little delicate because they ask me to speak to a meeting in Moscow. Therefore, many people will be listening, but I have to find a way to be equidistant. But I will ask maybe some of you to say hello or something like that. It's a short, it's 20 minutes.
What sort of meeting?
Eh?
Strictly scientific meeting?
Of course, absolutely. Nothing else. Strictly scientific. Not absolutely no reference to anything.
Beyond.
Black holes. My talk will be black holes all over the universe. And then the other one will be moment with, oh yes, the work of Fermi and Tukevich. And the Big Bang.
Yeah, I'm also kind of, because, for instance, they have asked me, no, it's a similar situation. So, these two. Huh?
Once?
No, my thing is, has to do not with Moscow, has to do with Argentina. The embassy has been Argentina, the embassy of Argentina asked me to do talk, do activity when I'm not in agreement with the government.
And not you know.
Tu hai ricevuto il mio messaggio? Mi manda caricato.
You understand?
Argentina in Italy.
No, to France, and France. And they is one of science. So
But this is the thing I would like to talk to you before we go, to see if you can convince Argentina to join Italy. That's
well,
what
you
Once we made some steps, but was not easy because
no, but it's not issue not to do. We need a single 2-3 sentence from you eventually, as the academy. 2 or 3 sentences, not more.
know, the Academy of Science,
Yes.
we are just 40 people. We are 40 active
Members.
members, active.
Yes, 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 yes.
And we talk about
No, but there's no collaboration with the government. But is to suggest that joining internet could be possible.
yes, well,
A sentence, a sentence, a sentence.
things that we can take something from them, he there, this fact that might be good.
Yeah, no.
Yes.
But the point is a statement by you to say it will be positive for Argentina to join the internet, nothing else. But from you,
Yeah, I have tried it.
okay, that is enough. One statement, statement. Oh, okay. We are still a few minutes. Ha preparato la mia presentazione, posso vederla, la prima pagina?
Mi ha detto di preparare la presentazione?
Elisabetta, quale libro abbiamo oggi?
amazing how they ask you this extremely calculation. Because you are
I know the yes.
Let's start.
So, but there are three present.
Yes, Maria Giovanna, you should speak first.
Okay.
And then the other one. Let's see. Sono in contatto.
Yes.
Yes,
Yes.
connected.
Okay.
I'm
Hi,
here.
Maria.
Hi. Nice to see you. Thank you for
Let's
inviting.
start.
Can you see me? Can you hear me well? Okay, perfect. So, shall I start sharing?
Wait a second. Just give us 1 minute.
Okay. Yes, of course.
What? There is some issue? Maria Giovanna, just wait 1 minute. We are solving some
No
issues and
problem
we'll let
at
you know,
all.
okay?
Yes. No problem.
Ok. Benissimo, ti si vede bene e mi fa piacere che partecipi e poi sentiamo anche i tuoi collaboratori.
Sì, grazie. Thank you so much for inviting me and also my collaborators, my students. Okay, so I will start sharing the screen. And
yes, you have 1 hour with all of you, no? You already split the time among yourself, no? Or should I?
Yes. Can you see the screen?
This what? Yes, we can see.
Can you see the screen? Okay. Let me just. Okay, so it is a pleasure for me now to introduce this the largest GRB optical catalog with non-redshift that you might have seen some results from RIDA in the previous Marcel Grossman meeting, but now I have the chance to tell you a little bit more about this catalog. So the beauty of this work, it has been that we have accomplished to gather 535 gamma ray bursts with and without color evolution, but all with non-redshift. And this is the first part, effort one of this analysis. So this is quite a huge effort. It took for us 3 years, and it is not only the analysis done by myself and senior scientists, but mainly it has been work done by students, 13 students, 2 PhD students, one of which Biagio got just his PhD a month ago in the middle of June, and 1 master student that now is Rida working with Professor Ruffini, and 10 undergraduate students all around the globe. And this is also thanks to the support that NUJ gave us in the past year. So now let's go, and also this paper got attracted attention by Monthly Notice, and we also had a press release issued by them. Okay, so why it is important to have the catalog, and why do we need for GRB cosmology, and what are the steps involved in compiling the catalog, what it is the color evolution analysis, what it is the rescaling factor, and I would like also to introduce the GRB LC Lightcore web tool. So, well, of course, the audience, you're all very well expert on a GRB, but I would like just to mention here that usually what we hear about is more on properties of the prompt emission and afterglow emission, but there is a huge amount of data, and usually it's up to 60% of data in X-ray that present plateau emission. This plateau emission is also present in optical, And indeed, the catalog gathers data from the Swift telescope, UVOT, and also from other 455 telescopes. And for a young student that may be in the audience, the cosmological origin has been accepted long ago. The farthest GRB observed is at redshift 9.4. These are extremely energetic and short events. They release the same amount of energy that our sun releases in its entire lifetime. And their spectrum is known. We distinct the X-ray, optical, and radio observation that can be observed up to several months from the main events. Now, why gamma ray bursts are potential cosmological tools? Because they can be probes of the early evolution of the universe. They are observed beyond the epoch of reionization, and they allow us to investigate population tree stars. Especially now that we have James W. Webb, that it is able to observe galaxies at redshift greater than 14, then we may be able to find even GRBs at that redshift. And so we can track the star formation. We are much more distant than supernova 1A. Currently, the highest redshift for supernova is at redshift 2.9, with a couple of them that have been actually located with James W. Webb when it was looking at the sky against same position, and quasars at redshift 7.54. So gamma ray bursts are still farther than those objects, but the problem is that they don't seem to be standard candles because their isotropic prompt luminosities span over 8 orders of magnitudes. And about the standardization of GRB, then Alexander Leonard is going to tell you more on this topic. Now, for 20 years, we have been struggling as a scientist to try to understand how to make GRB standard candle. So the challenge is here because the light curves vary very widely. So if you have seen one gamma ray burst, you have just seen one GRB. And here, this is the Swift light curve repository, in which you can see that the prompt emission are very variable. And so the point is that we could apply this standard candle to the prompt emission, but we can also look at the afterglow emission properties. And this is what we did since the end of my PhD. So I would like to also present some timeline of this relation and how this afterglow relation can be related also to the prompt emission properties and why it is important then for us the building of the catalog. So the prompt correlation with GRB discovered by Ionetoku, Amati, Ghirlanda, Susui are all related to the prompt emission. But this feature of the plateau, which ranges from 42 to 60%, which is the flattening of the afterglow light curve that I showed a moment ago, it's actually very important because it allows us to have the possibility to gather the 2D Dynoti relation, which is a relation between the luminosity at the end of the plateau emission and the rest frame time at the end of the plateau emission. But because we have also, this is an anti-correlation, so it means that more luminous the plateau is, shorter it is its duration. So it means that the energy reservoir of the plateau stays constant. And again, Alexander is going to tell us more about that. And then we have the peak prompt luminosity that is correlated with the luminosity at the end of the plateau emission. So those two relations are not only obtained with rest frame quantities, but also corrected for selection biases and redshift evolution. And indeed, you can see in this timeline that in 2018, I moved to Stanford University to work with Professor Petrosian, who is also part of ICRANET, to understand selection biases processes. And we discovered that these relations are actually not due to selection biases, but they are intrinsic to the GRB physics. So the challenge then, starting in 2013, became even more intriguing. And then we combined this 2D relation in one 3D relation, which is the combination of the two because they both have the luminosity at the end of the plateau emission as a common parameter. And this relation is again important as because it is already corrected for selection biases and redshift evolution. And then all this time I've been, after the PhD, I've been employed in Krakow, so, but moving back and forth from Europe to Stanford and then to Japan. And in the end of 2020, since I wanted to investigate more the aspect of the 3D and 2D relation in optical and radio, I moved to NUJ, where facilities like the Alma Data and Subaru could be available for making the most out of this correlation. And again, we obtained that these relationships are intrinsic to GLB physics and they are unbiased. So now this is the relation, the 3D relation discovered in 2013. As I was mentioning, this is a fundamental plane because it identifies a plane where the colors are the different classes of GRBs, and the classes of GRBs that are closer to the fundamental plane are actually the ones that better fit this relation, and these are the long gamma ray bursts with well-behaved plateau emission, which is currently relatively flat, so the angle between the end of plateau and the beginning should be not greater than 41 degrees. So this is a phenomenological relation. I mean, this is a phenomenological way to detect and to pinpoint a clean sample of gamma ray burst. This 3D relation, when we apply this cut as a reduced scatter of 24%, so this is practically, when you consider this gold sample, you have a reduction even of 50%, and actually this was really a boost forward in the analysis of the use of GLB relation as cosmological tools. And this analysis also got attention in the media. There was a press release by NASA, and also I was invited in San Diego in 2016 for this press briefing at the American Astronomical Society. So we were encouraged by these results, and we also continue on the optical analysis. We gathered 58 gamma ray bursts, and these 58 gamma ray bursts are also part of this catalog. And here are the several, this is without evolution and with the correction for evolution, and this panel below shows the Gaussian distribution from the golden sample, which is in yellow, that it has more restriction compared to the gold in the sense that it has no flares in the plateau and it has no gaps compared to the other sample. So from the optical analysis, we see there is no particular clustering of the GRBs according to the sample, but situation is different for X-rays in which the categories are actually clustering in different space in the they are actually having a difference in the zeta score. Now, what do we need for GLB cosmology? Well, either we can continue finding tighter reliable relations, either we can increase the sample size, having a cosmology independent approach, for example, via low zeta probes, and we had a recent paper with Arianna Favale last year with the cosmic chronometer, or we can increase the aspect of the physical interpretation, the connection with the theory in the quest for the standard set. How can we do that? For example, if we consider the precision with cosmology, and now a few years ago, we could see that if we consider only the optical sample, but with the same error bars, the precision of Skolnick can be reached in when you have like thousands of GLB. But if you have the simulation result for the optical sample with half the error, you can reach this even in with a half number of GLB or less number of GLBs. So when we had this somehow forecast, we were a little bit happy from one side, because, okay, again, this paper was published in 2022, so now it's already 3 years old, so it means that we are already here for this Betulle, so we have already reached the precision that, and I would like to use the pointer here. So we have already used the precision that the supernova people obtained a decade ago when we use the machine learning and light core reconstruction. And in fact, on the light core reconstruction, Kushik is going to tell us more. So I will not speak about that now. And basically, we could say, okay, we are a decade beyond, we are a decade behind the supernova in terms of precision if we consider the omega n parameter. And in this estimate that does not take into account the Einstein probe telescope, does not take into account the Subaru Ultimate and the future LLST and the observation by the other incoming by the Roman Grace telescope. This is the weight. We will need to wait 17 or 18 years. But that's not the case because we have many things that we can actually do in the sense that we can improve our machine learning analysis, and we already did since 2022 because at that time we could increase the sample by twice. Now we have an increase of the sample by 110%, and there are now works that we are tackling for which we are confident we can reach a larger sample of gamma ray bursts, so with higher precision on machine learning, so we can actually increase more the sample size combining X-ray and optical. And then there are also advantages in the light core reconstruction that Kushi will present. So because of that, now the point is that we would need to have more data in optical to actually have induced prediction, a better prediction for cosmology with the 3D relation. And another news that we are working also with Alexander and the group from UK is that we are also comparing the value of W. So if we consider the equation state parameter, and we can reach this in a much less number of years. So it depends on which parameters of cosmology do you want to tackle. Now, this analysis, as I mentioned, of the telescope gathering was quite huge because we gathered 455 telescopes from 570 instruments, and we have even the campaign from the KISO, that it is a telescope of aperture of 1.05 meter at redshift 3.6, and we have all gathered all the release from Japanese telescope. We have recalibrated the data, and so we are also discussing the joint avenue between KISO and SVOM. This product is accessible via web app, so you can take the light curves, you can download them all, or you can download one by one. Then you can expand this information, and here you can by yourself calculate the spectral index. Here on the right hand side of the figure, you have the bands, and we gathered all the possible bands, all the possible filters that were present in the literature for the observation of that given gamma ray burst. So for each of the photometric data point, we have the information from where this has been taken. Now, from the 535 GRBs, the 30% of this comes from the Swift U-boat, but the rest actually comes from all the ground-based telescope. And the point is that because in the machine learning analysis so far we have worked on the X-ray, but to generalize the sample, but not yet in optical. So we are building. The plan is to build the same catalog, but with the gamma ray burst without redshift, so that we can also increase the. We can actually build the generalization set. Generalization set is a set of gamma ray bursts for which you don't have the redshift, but you have all the properties that are necessary to infer the redshift. And so this is also a call for the ICRANet group, or for people that now are listening to the talk, that if you are interested in joining this adventure, the next step of this adventure, please let me know. Or if you have even more small aperture telescope, please again join this network, because this is also an effort that we are making for the community to have this uniform format in the catalog, since all the information are rather sparse. And we also highlighted the importance of the Japanese telescopes in our work. Indeed, we have data from all these telescopes and many more. Now, the future perspective, and we have gathered 33 new gamma ray bursts with non-redshift up to the end of January 2025, but more are coming up, is that we would like to then revert this from magnitude to flux, but we are trying to consider a conversion that takes into account all the bands that are used, not only in the single filter. So this is something that it is new compared to what it is done in the literature. And when you do a quick look, we provide the right ascension, the declination, the redshift, and the spectral index. And we color the points according to the different band. Now, why it was so important for us to consider also the Subaru data? Because, and this is actually also the call for any other smaller aperture. This is of course 8.2 meter telescope, but if you consider smaller aperture telescope that can fill the gap for the plateau emission, even one data point, even few photometric data point, is going to tell you whether or not, for example, there is a plateau over there. So we can provide spectral information, we can have the redshift determination, and we can identify new plateaus and reduce the uncertainties in the error bar. Let's say that this data point would be placed here. In such a case, we would obtain smaller uncertainty in this region. But basically, we can reveal new plateaus, and therefore we can actually increase our sample size for the machine learning analysis, because the machine learning analysis is based on the plateau features. Now, this catalog will not only help for correlations, as I said already, for the redshift estimate, but will also help in the light reconstruction for optical that will be much more challenging of the one in X-ray. And regarding the redshift estimation, Milind is going to tell us about the catalog that we had built for the redshift inference. So we have we can use the catalog also to look for kilonova events. We can also understand better the dichotomy between long and short GRBs, and we can use for population studies. And another point is that we can go towards the early universe, so we can tackle, for example, the different GRBs from low redshift and high redshift, how they look like, the morphology, and so forth, to investigate future population study POP3 stars. But the community needs a uniform format for data sharing and circular notices for this event. So we collected data from the GCN, from IATL private communication, from other paper. Then we homogenize the sample. We shift in AB system and apply the galactic extinction correction. And where possible, we also apply the K correction and the host galaxy correction. Then we identify whether or not the GRB have color evolution or not. And then if it doesn't have color evolution, we rescale it. And then we divide the GRBs into the group. So whether or not they agree or disagree with the literature, or they are undetermined by us. When we homogenize the sample, we correct for the galactic reddening using the Shuffle and Asiago database. We transform from magnitude in AB system, so we overcome the fluctuation of the filter 0 point. We apply the K correction where the spectral index is available, or where we can actually determine our own spectral indices. And then we apply the Austin correction using the pale extinction curve. Now, this is a sketch of what we did. So we have 535 GRBs. In the step 1, we have 4 coincident magnitude in different filters. If we do have those, we are going to compute the spectral index, and so we have 143. Then we use the K correction, but 5 GRBs are removed for K correction discontinuity. And out of those, we can say that 397 GRPs are without this K correction. But in step 4, we remove these 4 GRBs with unconstrained p-value, so we end up with a sample of 531. And then we have the color evolution. So it's we have 2 methods for the color evolution, either with slope that is variable or slope is equal to 0. And I will tell you in a moment about that. So how can we determine the color evolution? So basically, here we have the several occurrences, and we wanted to remove the time duplicates, the magnitude that have the same time duplicate. So if the time is exactly the same, this is easy to be done. But when we have that the time is not the same, and we need to rescale these data points, it's hard for us to do without a given criteria. First of all, we need to choose the most numerous filter, which is the I filter in this case. But then you could also take a reference filter as the R, for example, because usually in all these 535 GRBs, R filter was always the most numerous. But in the web app, you can choose what filters you need. And then, after trials and error,
Scusami un momento, perché
sì,
abbiamo la visita del sindaco, che è molto
sì,
impegnato
sì,
e che ha avuto la cortesia di venire.
sì,
Quindi interrompiamo per una decina di minuti e
sì,
poi diamo i 10 minuti dopo. Va bene per
va
te?
bene. Sì, sì, certo, non c'è problema. Ok,
It is a pleasure to have with us today the mayor and some of the people, alcune delle persone più qualificate sono presenti, chiaramente Wang e gli altri, e lui viene un nostro precedente collaboratore che adesso è professore in Argentina. What is Felix? Can you call him? Can you call him?
Yes.
Narek dall'Armenia, Egori da noi, Dadi ci siamo. Ed è un grande piacere vederti, siamo in grande attività perché siamo un po' connessi in tempo reale con tutti gli altri gruppi e oggi anche abbiamo un altro incontro delicato, importante, perché a mezzogiorno daremo un saluto a un convegno internazionale che si tiene a Mosca. Però la persona più importante che abbiamo è il professor Dili, che che adesso gli si come?
But he will come in a few minutes. He is chairing a meeting of his university now, online.
Online. È bloccato da lui viene dalla più grande università di Pechino, il professor Di, e ha creato il più grande radiotelescopio al mondo. E siccome riesce a vedere in tempo reale una quantità di dati impressionanti, unico, ed è oltretutto parte della collaborazione radio e radiotelescopi in tutto il mondo e quindi è un grande onore averlo qua con noi. Oggi alle 3 andremo a salutare il rettore. Quindi se per caso lui è ancora preso dalla sua conferenza di lavoro, ti veniamo a salutare più tardi per fartelo conoscere.
Va bene. Va bene. Più tardi quando?
L'ora che ti fa più, prima di andare dal rettore, per esempio.
Stamattina, diciamo.
Stamattina.
Vediamo un po' a che ora può.
A che ora potrebbe essere?
Verso l'una.
Verso l'una. A l'una io devo. Oggi
dovrebbe andare alle 2:40, però ho chiesto di anticiparlo alle 2.
Sì.
Vabbè, all'una, mezzo, 10 minuti da me. Poi...
all'una.
Che ora finisco il primo intervento?
Alle 11:30.
Alle 11:30, va bene.
Anche a mezzogiorno, se vuoi.
Va bene.
Va bene a mezzogiorno?
Alle 11:30 dovrebbe finire il suo primo intervento.
Sì.
E poi dovrebbe esserci un po' a pranzo dalle 2 in su.
Va bene, ti veniamo a mezzogiorno.
Va bene. Anche mezzogiorno e un quarto, insomma, vabbè, mezzogiorno.
Sì, perché ci tengo molto, che è uno dei più grandi scienziati al mondo.
Va bene.
Veramente impressionante.
Io vi auguro un buon lavoro, non voglio levarvi tempo alla vostra attività, quindi vi auguro buon lavoro. Per noi tutti quanti sanno che questo centro è fondamentale per quello che produce al mondo e per quello che dà alla nostra città, quindi grazie per quello che fate, perché certamente il vostro lavoro contribuisce alla crescita del mondo in generale e anche alla pace del mondo, che oggi è fondamentale. Quindi auguri, complimenti. Voi dovreste essere, siete i nuovi Prometeo, il Prometeo del XXI secolo, quelli che prendono il fuoco dal sole e lo portano agli uomini, per far sì che l'innovazione, la ricerca, le scoperte possano contribuire al benessere di tutti. Quindi auguri e grazie al professore.
Ti ringraziamo di cuore, però credimi, c'è una situazione strana, perché nelle ultime ore stiamo cambiando la fisica. E ti faccio un esempio, Nave. Ieri abbiamo avuto delle presentazioni dalla nuova sede che si è collegata con noi, da Tallinn e dall'Estonia. L'Estonia adesso è dentro l'Icranet e quindi è un passo avanti notevole, l'Università di Tartu. Ma abbiamo avuto una presentazione su un buco nero di 10 alla 10, cioè 10 miliardi di masse solari, e ci hanno presentato dei dati che hanno ottenuto. Lui ha visto questo oggetto e domani o oggi stesso ci farà vedere le immagini di questo oggetto. È una cosa impressionante, cioè stiamo vivendo realmente questa nuova realtà. Can you tell us a little bit about JC, just a few words?
I can tell a few more, but I think
No, but you explained the exceptionality of this system and that you have been able to see it.
Yeah, the exceptionality is that they are claiming that there is double black holes, two black holes that are rotating, and they see these periodic changes of the signal. So if this periodicity is really present, it means that there is something that is orbiting around each other. And they claim that they are able to observe the gravitational waves from the system.
Ma la cosa impressionante è che possiamo vedere queste cose. e loro ci faranno vedere le immagini.
Va bene. Buon lavoro allora.
Ti ringrazio. Felix è uno dei grandi scienziati al mondo. È venuto a pescare di origine argentina, ma lavora a Parigi. E i più grandi getti dell'universo è lui che li ha scoperti. E stiamo cercando di capire la macchina che produce. Questo è un momento veramente emozionante. È fantastico averlo qua con noi. Okay?
Allora ci vediamo dopo.
Ci vediamo dopo, vediamo verso mezzogiorno.
Sì.
12 o'clock we go to see in the office. Together with the is okay with you? Yes? Okay.
Arrivederci.
Ciao. Scusa.
Okay. No.
Ma
No problem at all.
Adesso ritorniamo a te, ti ridiamo 10 minuti.
Quanto tempo ho in generale? Perché poi vorrei appunto che parlassero anche i miei collaboratori. Quanto tempo ho adesso? Recuperiamo oppure allo stesso tempo? So we are going to make up
In
for
original
this
plan,
time
you
or
have still
not?
like half an hour, but given we had like 10 minutes break, I think you have like 40 minutes, so you can
40
share the
minutes.
time among
Okay.
yourself, okay?
Okay, perfect. Thank you so much. Thanks. Okay. So can you see the screen?
Yes.
Okay, so let me just from current slide. Okay, so then I was saying that the importance is that we have this uniform format for the GLB optical data. And so we have the magnitude error, the filter, the system. Of course, we have already provided in AB system, but originally we might have different system in the data. And then we have the observatory, the telescope, and the instrument used, so that people can go back to the specific of the instrument and telescope, and then whether or not there is a galactic extinction correction. If it is not present, then we're going to apply, and then the source, this is GCN or the paper. And then we flag the points, whether or not there is some problem. For example, if there is a yes flag, it can be there are data points that are outliers because maybe there is an error on the observation, or it's like the calibration is off, and we somehow search for this for the reasons for which there is this flag. So people could even discard the point or have a look themselves. So now I said that the rescaling factors is not an easy task to be found. So basically we had to consider what it is this difference in magnitude and how this difference in magnitude should be converted in different in time. And basically we have that then the time of the filter minus this generic time divided by the time of the filter. So it is a relative time should be less than 2.5%. Why 2.5%? Because basically this is the difference in magnitude on the error that you will find in the distribution. So we are taking the peak and half width of the peak. We are considering that after that, that this difference is going to be substantial. So the magnitude peak error at 5%, and then we take half of it. Now with this factor in mind, we could consider also the spectral index, and here we use this, I already discussed how to obtain the spectral index, and here we have the case of 080928A, and here the several data points as a function of lambda. Now, what do we do with the spectral analysis? Because I mentioned in the beginning that we also can use the catalog for actually detecting checking, for example, the modeling, and we could check the standard Farbol model or other model, and we could consider spectral index, whether or not it is the spectral optical index is equal to the X-ray index, or the optical is equal to X-ray minus 0.5, according to whether or not, so the green line are the optical spectral index that follow the equality minus 0.5 relation, while the red one are the ones that respect the same equation. Then the respective red line and the green line, they have the belonging to this equation. While the lower panel consider the data that respect both relations, so there is the degeneracy, and also the ones that respect neither of the two. Then we consider two samples. The gold sample is the sample for which we have the achromatic behavior characterized by color evolution or the absence of the color evolution, and it aligns with the finding from the literature. And the other characteristic is that if the chromatic behavior is determined in this work, is maybe due to an increased data set compared to previous analysis. And then we have the diamond sample that we have the spectral index but no color evolution. Now with this analysis in mind, we can obtain the color evolution analysis. I was mentioning we have two cases, or we fit with the simple power law, either A equal to 0 or A is variable. But regardless of the situation, analysis of the result is similar. We can see here we use the Levenberg algorithm, and here it is the residual for this fitting. So these results are saying that there is some agreement with the literature, totally disagreement, and some apparent disagreement. So the apparent disagreement means that we have, for example, different filters from the literature, and when we compare the same filters, actually this disagreement disappears. Now we can see that the analysis with the fit with A equal to 0 and A variable are somehow consistent. But the problem is that we have many cases that are still undetermined. So if we consider the A variable and the A constant, we can see that there is equal preference. So there is really not, it is not so important the method that we use, rather the results that we have. And as I mentioned, one of the plague here is that we have still many cases that are determined only by us and not in the literature. So this is something that we are gaining with the catalog, 39%, 36%, but many are still undetermined. So this is the group division that we have with no color evolution, and undetermined bias. And this is summarizing the comparison with the literature in the two samples. And because I would like to give a bit more time to the students, I would like to leave you with this image of this web app that includes all the GRBs. And if you can click on it, or you can have the barcode, you will be able to basically download the data. And now I will just introduce, but then Kushi will tell you a little bit more about this light curve reconstruction. We had several machine learning method and deep learning method to fill in the gap in the light curve based on the catalog of 545 gamma ray bursts. We divide the sample in four parts: good, the GLB that have flat plateau, the ones with break, the one with flares and bumps, and one with flares, bumps, and double break. And here it is the analysis with what we are achieving is that we have an uncertainty decrease that has several percentage. And we have also the outlier percentage, so how many GRBs do not follow this, they practically are not well reconstructed by this method. And we apply the five-fold cross-validation method. And these are the good GRBs, so the one that have flat plateau. So now I'm going to present this one because then Kushi is going to tell you that we have even more appealing news compared to this analysis. So basically here we have a reduction of up to 41%, and Kushi has found about 61%. This is the analysis with the several light curve. So thank you so much. So if you want to share light curve, new ideas and tool, please contact me. Thanks. I'm open to questions. Hello? Can you still hear me?
Maria Giovanna, how many
Yes.
of these optical data you have the redshift?
So all of them, we have the redshift. So the next plan is to gather all gamma ray bursts without redshift. So currently we have 535 in the release and about 60 that is going to be added to this catalog. So we have practically almost 600 GRBs with redshift.
500 with redshift. And always the description you make is in the rest frame of the source.
The description I'm doing it is in the observer frame because currently this analysis has been done with the observer frame quantity. We still have to do the next step that it is the the part 2 of the catalog in which we are going to first move from the magnitude to flux space and then from flux to the luminosity. And then with the luminosity, we can investigate mathematical modeling and also have the analysis of the relationship.
You've got mail.
Sorry, Professor Ruffini, I could not hear you the question. I could not hear the question.
Okay, I can say something about the last two slides about the machine learning. Because
Yes.
Maria, you went very fast about the last two slides. I didn't understand the method.
Well, in the for the machine learning is going to speak more Milind. I don't want to take Milind floors for that. So the machine learning is an ensemble method, the super learner that is going to use several variables that we have in this catalog, including the plateau emission, to infer the redshift. So you have 9 properties of gamma ray bursts that are going to be used for which you have the redshift, and then when you have this generalization set, so the generalization has no redshift, then you can infer the redshift out of these properties. But Milind will tell you more about that. Thanks for the question.
It would be good if you can spend 1 week with us to check with this rest frame luminosity.
Yes.
Anytime in the August or whatever would be splendid.
Okay. Yes, I will check my schedule and we can discuss this. Yes. Thank you so much for the invitation.
I have one question.
Okay, thank you very much. So we move to the next presentation, which is again online, no? Kushi Gupta, Machine Learning Analysis of Reconstructing GRB Light Bursts. Can you please share your screen?
Hello. Good morning, everyone, who are all present here. Thank you so much for inviting me to Extranet. I am grateful to be presenting the machine learning analysis on gamma ray burst light curve reconstruction. Thank you for Maria for such a detailed explanation on the GRB catalog. So let's just get into it. So the goal here is to reconstruct the gamma ray burst light curve using machine learning and statistical methods. Since Maria has already outlined the potential of GRBs as standard candles, this research is highly important because the data set that we have as of now, the graphs are incomplete and we have a lot of gaps. These are generally because of follow-up details and equipment limitations. So we're trying to tune them down using reconstruction methods using machine learning analysis. GRBs also have a huge potential that can provide insight into population 3 stars. And the main goal of this research is to tighten the 2D dynamic relation between the end rest frame time of the plateau and the respective luminosity. So what we're trying to do is we are trying to decrease the uncertainties of the three main parameters of the GRBs, which are LA, TA, and alpha, by comparing it to the original Villengale model and fitting our new models to the original model. For example, this is an original data set that is observed from the SIFT repository. This is the X-ray emissions of a GRB. And as you can see, there are like many gaps in this, which are not efficient for redshift analysis and for further studies on the particular GRBs. Previous two papers that have already been published on this method are Manchandana et al. 2025, which introduced 9 models for GRB construction. And the best model was the Biomamba model, which reduced the uncertainties by 25.9 for TA, 28.6 for FA, and 37.7 for alpha. These were compared to the Villengale model over the 545 GRB sample that was obtained by the SWIFT repository. The next paper that we worked on was the Kaushal et al. 2025, which we also worked on 6 new models, and the isotonic regression improved upon the previous best model that was by Mamba, and the new metrics for the uncertainties were 36.3 for TA, 36.1 for FA, and 43.6 for alpha. For the new latest paper that we're working on, we've introduced 4 new models, which are kernel-rich regression, symbolic regression, cubic spanning smooth, and Gaussian processes via ANN. Let's get into all these models one by one. Kernel-rich regression is a type of ridge regression that it combines ridge regression with the kernel trick to model nonlinear relationships in data. Ridge regression is a type of machine learning algorithm that deals with collinearity in all sorts of collinearity in different varied sorts of data. So it just basically it learns a linear function in a high dimensional feature space without directly transforming the input data into that space. So we're learning the feature space without actually learning the input data. We're forming the feature space without getting any pre-analysis or pre-knowledge about the input data that we're feeding into the model. So thus it also reduces overfitting due to this method, and it has built-in regularization, which is like also very important for uncertainty built-in data such as astrophysical data. And it is also very efficient in capturing nonlinear temporal and flux variations. The results of the kernel-rich regressions are displayed here. This is for a GRB with breaks in them, as you can see. And it has efficiently formed a smooth architecture over the observed data points. And we cannot see any random dips or random glitches in the data that we would not prefer as a result of these ML models. Next, we have the final result for the KRR model, and we have achieved the highest uncertainty reduction as far as all the 16 models that were introduced in the last 2 papers. And the numbers are 61.9 for FA, 61.3 for TA, and 67.2 for alpha. These are like the best uncertainty methods that we have achieved as of now. And for further studies, we would recommend as KRR model as a baseline model for reconstruction of GRB light curves. Next, we have the symbolic regression model. It is a kind of model that works on several mathematical expressions, and it does not assign one particular expression for one GRB. It just searches through its database of several expressions and fits each one to the dataset and finds out which one is the best fit. For this model, we have also incorporated genetic programming, which has proven very important in the analysis of GRB light curves. The three measures of the GP programming are selection, crossover, and mutations. Crossover combines portions of 2 expressions, mutations which randomly modifies expressions, and selections which selects the best performing expressions. For the symbolic regression model, first we analyzed with the 1,000 iterations, but it resulted in 34 exceptional GRBs. But later with 2,000 iterations and MPI integration, we achieved like good results for them as well. These were the results for the symbolic regression model, and these are like the favorable results. This is a GRB with a long gap in it, and these are GRBs with flares as well as gaps in it. As you can see, we have achieved a very smooth transition over the observed data points, and did not overfit the data, and you cannot observe any random fits, random depths in the reconstructed graph as well. Next, we have the final results for the uncertainty decrease for symbolic regression model. It has also proven to be a general reliable reconstruction model, and has also surpassed the previous best model, which was isotonic regression. By factor of FA, we have achieved 34% uncertainty reduction. For DA, we have achieved 33%. And for alpha, we have achieved 52%, which is incredible for the third parameter. Next, we have the cubic smoothing spline model. This is a model that essentially works on the third differential function of the cubic polynomials. And unlike interpolation splines that pass through all data points, smoothing splines allow for more deviation from the data. So this allows us to achieve a more smoother curve rather than simple interpolation spines. And it is also very suitable for dealing with noisy data, which we encountered a lot in GRB data curves. These are the reconstruction results for cubic smoothing spline. This is a general good GRB, and this is a GRB with breaks in it. As you can see, we have achieved a very smooth reconstruction without any dips or errors. So this was another efficient model for reconstruction. Next, we have the uncertainty decrease. This is also surpassed the previous best model, which was isotonic regression. And the uncertainty parameters have decreased a lot by 47% for FA, 46% for TA, and 54% for alpha. This has proven to be a very reliable model for GRB reconstruction. The final model that we have is the GP ANN model. In the previous papers, we utilized GP and deep GP processes, but in this we thought let's combine neural networks to the GP strategy. So since we are dealing with a lot of uncertainty in GRB reconstruction, Gaussian processes turn out to be one of the best methods that we can use because it has inherent uncertainty within the model itself. So by incorporating it with the ANN, we decided to do a model with two hidden layers with each head signifying the mean and uncertainty for each input in the GRB light curve. So for example, if the input is given for the first layer outputs two heads which are mean and uncertainty, and these are fed into the next layer. The final output of this is a probability estimation, and from which we find out the mean, like the mean and the variance. So since traditional models assume constant variance across input, which can lead to generalization, this performs better than traditional GP models. And this also has proven to perform better than the deep GP model. It captures the probabilistic spirit of the GPs, and it is very expressive, and it can model complex non-linearities in the GRB flux evolution. These are the reconstruction results for the GPVINN model. This is for the good GRB, and these are for GRBs with breaks in them. As you can see, compared to the previous models, we have a lot of uncertainty tied into the model itself because GP via nature is a very uncertain model. So you can see wider confidence intervals in the reconstruction graph, but still we do not assume any unfavorable outputs.
A bit late from the time schedule, okay? If you could little bit speed up.
Okay, sure. So these were the uncertainty decrease for the GPVINN model. And this is also proved to be a very reliable and a journal model for the construction. For the final results are the kernel-rich regression model has achieved the highest uncertainty reduction, and these are these are like the values that we mentioned before. And the GPVINN model has shown notable improvements across all GRB parameters, and it has also achieved the lowest outlier rates, which signifies excellent generalization capabilities for a model. And all the 4 models analyzed in this paper have consistently performed better than all the 16 models that we worked with before. This is the final analysis table. As you can see, the 4 models, KRR has performed well than all the previous models, and the GPVINN has achieved the lowest outlier rates from all the previous models. And for the good GRBs also, all the 4 models have achieved 0% outlier rates for the third parameter, which is alpha, which signifies their excellent generalization and reconstruction capabilities. Next, we aim to apply these further machine learning methods, which are like physics-informed neural networks, because we have found that informing the model on how the Dynothy relation works physically has proven to be beneficial. And we also aim to extend this research using transformers with other data sets, with further data sets like the Einstein probe. Thank you for your time. I am open to questions now.
One short question, if there are any. Okay, one view.
Arvinda, about the symbolic regression, you are fitting all the light curves by one function with 3 parameters, or you are fitting the light curve one by one with independent functions?
I'm sorry, it's not audible.
Before the symbolic regression, you are fitting all the GRBs by one function, or you are fitting each GRB with a different function.
We are fitting each GRB with a different function because we are training each GRB separately. We're not training a batch of all the GRBs. So the model fits the best mathematical expression on the particularities based on each GRB.
But maybe you would like to add that the fine-tuning is done for a bunch of GRBs and it is not going to be changed. So the fine-tuning is done for, we take 16 GRBs, and out of these 16 GRBs, 4 of them, they belong to these 4 categories that I and Kushi showed, and the fine-tuning parameter is not going to change from after it is settled in the beginning, regardless of the model that we are going to use.
Okay, thank you. So now we move to the next presentation. So it's
thank you so much.
Alexander Leonard, the GRB plateau and record spin down. May I ask you to fit in 10 minutes, so we'll not...
Yes, yes.
Okay?
Thank you very much for having me today. Okay, can you see my screen presentation?
Yes, we can.
Okay. Thank you very much. So I would like to give you highlights of our recently published paper in Journal of High Energy Astrophysics this year under the title The Multi-Wavelength Correlations Quest for Central Engines of GRB Plateaus, Magnetar versus Black Hole Spin Down. Okay, so let's start with a brief reminder from the Maria's talk. This is a typical GRB light curve, which has a very nice data coverage. So first we have very chaotic prompt phase, which is also very luminous, and it is followed by a rapid decline in the luminosity. At later time, some GRBs show afterglow emission, and in this set there is a subset of GRBs which show also a flat part in the light curve, the so-called plateau. It is widely discussed in the literature that this phase is likely a signature of a prolonged energy emission from some central engine. So in this paper, we asked ourselves the question, how exactly do we generate the plateau in some rather peculiar GRBs? Okay, so for almost 30 years, we already have a model of neutron star magnetar powered plateau. The magnetar is born rapidly spinning with very high magnetic field, and it's losing its kinetic energy and converts it to the electromagnetic radiation via dipole emission. And this model fits a lot of data very well. It can explain the plateau. It can explain also the Dynoti correlation, the 2D one, which Professor discussed, and I will also discuss later. However, it has one major shortcoming. Neutron stars have an upper energy limit. Because they cannot be too massive, because they would collapse into the black hole, and they cannot spin too rapidly because they would shed mass from the surface. And indeed, we did observe, many people reported in the literature, cases of GRBs which exceed this energy limit, a maximum energy limit of magnetars. So a black hole engine is needed to power such cases. Inspired by this argument and by the very recent findings in the literature that the MAD accretion, magnetically arrested disk accretion, leads to spin down of the black hole. So if the black hole is born rapidly spinning and the magnetically arrested disk forms after some time when the plateau begins, then the simulations show that a delivery of angular momentum from the disk to black hole is very ineffective because the magnetic field interacts with the disk. It causes turbulences and causes the disk to lose the angular momentum. So in those conservation equations, the energy conservation equation and angular momentum conservation equation, the extraction factors dominate, like the magnetic torque factor or the energy loss through a blunt Fortisnaic luminosity. Those equations can be solved for the luminosity as a function of time for a given functional form of the accretion rate. The simplest thing we can do is to assume a constant accretion rate, which can be approximately true in case of the collapsars, which have an extended envelope, which can produce such an accretion rate. And that's what we numerically obtained. We perfectly recover the flat phase followed by a rapid decline. We can obviously vary the parameters. We can vary the black hole mass, the accretion rate. We can choose a different functional form of the accretion rate and different initial spin of the black hole to obtain different shapes, different luminosities. Moreover, we can produce some extra features like flares through a single events of magnetic reconnection. Bumps can be a result of an increased accretion rate, over some small period, and we can further control the shape with a different functional form of the accretion rate. Okay, so this model can be actually used to measure the black hole mass which is born in the GRB event and the accretion rate. It still suffers a little bit from the uncertainties because we have measurements of jet opening angle for very few sources and the shock radiative efficiency for a very few sources, but it is possible to do that for now, small sample, which can be extended in the future. This model has another advantage, that it matches the observations of black holes from gravitational waves. What was surprising, what the LIGO team found 2 years ago, was that the black holes that we observed via gravitational waves have very low spins, and it was contrary to our predictions. So the fact that black holes can be born at the end of the GRB can have spin very close to zero is a perfect match for the observed distribution from the LIGO measurements. Okay, this model has another advantage, just like Magnetar. It does recover the Dynoti correlation as well. The Dynoti correlation relates the luminosity at the time of at the end of the plateau and the time which passes from the beginning of GRB until the end of the plateau. And via the black hole model, assuming a reasonable range of black hole masses, a reasonable range of accretion rates, I can reproduce most of the space in this luminosity duration parameter space occupied by the sources. So we spoke about collapsars. What about neutron star mergers? Well, it is quite hard to have a prolonged accretion rate in neutron star mergers because they don't have extended envelopes. So it is often considered in the literature that if a plateau in such GRB exists, it is a result of an actually spin down of very massive magnetar. We can pinpoint GRBs from mergers through a kilonova emission. So we indeed decided to compare the kilonova associated GRBs, the yellow stars, with the collapsar GRBs, the gray dots. And we notice that there is a 2 orders of magnitude difference in luminosity, as you can see here, between the two samples. They both follow anti-correlation, luminosity time anti-correlation, but with different normalizations. So if the mergers actually produce a very massive neutron star with a mass of a typical result of neutron star merger around 2.3 solar masses, then we can kind of use this estimate to calibrate this parameter space and estimate what should be the average black hole mass produced by GRB. Okay, thank you very much for your attention. I hope you found it interesting. You can check the original manuscript here.
Okay, thank you very much. Question?
Can I see the first picture that you showed, the first figure? Okay. You see, what we are learning, and we will send you a recent paper, that the first second of a GRB in the rest frame are not yet dominated by either the black hole or a neutron star, but they are other phenomena. In particular, the spike that you see is very much related to the UP, which will be the topic of the next talk by Moradi. Therefore, it is important that we discuss with your group as soon as possible in order to differentiate what really is the optical emission from the power law region, from the spiky region in the first 10 seconds.
Yes, I totally agree. I discussed the black hole and magnetar as the reason behind the afterglow. The prompt phase is a completely different story. And this is in X-ray, actually. Sorry for the confusion.
Is the UP. I think we will have next talk by Moradi on that. Thanks.
Thank you.
Yes, thank you. So let's move to the next presentation, which is Milan Sarkar, Machine Learning, Redshift Inference and Classification and Associated Web App. Can you please share your screen? Please try to fit in 10 minutes. No, we are a little bit late from the schedule.
Sure. Hello everyone, I am Milind and I am a third year undergraduate student at ISER Mohali. Today I am honored to deliver this talk on gamma ray burst redshift estimation and classification using supervised machine learning. This presentation.
But Milind, we cannot see the screen.
What?
We cannot see the screen. I think I cannot.
Just a
Milind,
second.
are you sharing the screen?
Yes. Just now can you see my screen?
No, but are you pushing this button share? Okay, now we can see. Thanks.
Yes, this presentation is based on a series of collaborative works conducted with Dr. Dainuti and other collaborators. GRBs are the most luminous electromagnetic events in the universe, as already told by Dr. Dainuti. So I won't be rather emphasizing on this, but still, GRBs offer a powerful tool for probing early cosmos, and the most distant burst is known at redshift 9.4. Theoretically, their brightness allows them to be observable out till redshift 15, making them prime candidates for exploring epochs such as cosmic reionization and formation of population 3 stars. However, despite the immense potential of GRBs for cosmological investigations, a significant observational bottleneck remains, which is the lack of spectroscopic redshift measurements. As of 2024, only around 12 to 26% of GRBs detected by satellites like Swift and Fermi have confirmed redshifts. This drastically limits our ability to study the intrinsic energetics and build a reliable luminosity function to explore the cosmic GRB formation rate. To address this issue, our research aims to provide redshift information for a larger fraction of GRBs by using their observable properties. We adopt two machine learning approaches: supervised regression for redshift estimation and binary classification for early identification of high redshift GRBs. This talk outlines the methods, results, and scientific implications of our work as presented in three major papers, two already published and one is to be submitted. So the first part of our project is already published in Astronomy and Astrophysics, led by our collaborator Aditya, which focuses on estimating GRB redshifts using plateau emission features in the X-ray afterglow observed by Swift XRT. The plateau phase, which is a relatively flat segment in the light curve before a steep decay, appears in roughly 38% of long duration bursts. It has been previously studied for its correlation between the plateau end time and luminosity, forming the dynautic relation. We developed a supervised regression framework using a broader set of observables. Our regression model uses superlearner ensemble, which combines several base learners, including linear models, support vector regressors, random forests, and gradient boosting machines into a model optimized via cross validation. The features fed into the model include prompt emission properties such as T90 fluence, peak flux, and photon index, plateau characteristics such as TAFA alpha beta, and hydrogen column density NH. All variables are log transformed to mitigate skewness and dynamic range issues. The target variable is log 1 plus z, which allows a more stable regression and improved predictive behavior. Here you can see a scatter matrix plot showing the distribution of the features involved and other distributions. So we trained our model on a sample of over 150 long GRBs with known redshifts and well characterized X-ray plateaus. Using this model, we estimated redshifts for around 276 GRBs that lacked spectroscopic measurements. Model performance on a validation set was excellent, with a Pearson correlation coefficient of 0.902 and an RMSE coefficient of 0.59 in log 1 plus c, where bias was 0.002 and NMAD was 0.46 with an outlier fraction of 8.57%. He also applied bias correction model that aligned predictions more closely with the true redshift values, especially at high Z, significantly reducing systematic offset. These are some results of our tenfold CV 100 times using the superlearner model, and is in line of what I said, as you can see in the plots. This was using balanced sampling. So to test the robustness of our model, we conducted a Monte Carlo simulation consisting of 200 trials using random subsets of data with sizes 14, 28, and 42. In each trial, we retrained the model and evaluated the same performance metrics. The median R remained above 0.75 even for the smallest subsets, and the distributions of RMSE, bias, and NMAD were narrow and well behaved. This confirmed the statistical stability and reproducibility of our regression pipeline, which makes it suitable for early mission data or instruments with limited GRB samples. Also, to ensure broad scalability, which we implemented a web-based application where users can input the features and get redshifts along with uncertainty estimates, which I'll show towards the end of the talk. Here are some plots related to the MCMC simulation we did for a robustness of our model. As already told, log NH, the column hydrogen density, was the most important feature in determining. So The second component of her research was redshift classification, as published in Dynoti et al. 2025 in APJS. Here, the objective is to classify GRBs as high Z or low Z using observable features alone. This has direct implications for telescope scheduling and resource allocation, since high Z GRBs must be followed up quickly before they fade below the spectroscopic detection limit. We constructed a classification pipeline using 251 Swift GRBs with plateau emission and known redshifts. Multiple redshift thresholds were considered, such as redshift at 2, 2.5, 3, and 3.5. The input features were the same as those used in regression task. The classifier was again implemented using superlearner ensemble, and pre-processing steps included estimation for outlier removal, MICE, which stands for multivariate imputation by chained equations for handling missing data, and SMOT, synthetic minority oversampling technique, to balance the training data when high C.
Can you please try to summarize, because we are time
Yes,
is
yes,
efficient, but
yes.
we said you are in half of your
Among,
slide.
yes.
Try to stop it, finish in 2 minutes, okay?
Okay, so among our 4 test configurations, mice only SMOT and mice plus SMOT, the best results came from SMOT, where at 3.5 redshift we achieved a sensitivity of 89% with an AUC of 0.95, as shown in this plot. This model is capable of robust generalization and effective high Z
Milind,
flagging.
I think because you have only 2 minutes, I would suggest, why don't you show the web app, okay?
Okay,
Because you have
so
only. That's okay.
yes, this is the main working of the web app and our model for the X-ray. First, when the user puts in the data, it goes through data cleaning. So we had given 251 GRBs, and we got about after data cleaning, we got around 178 GRBs, and then we offer our user options of using M estimator or mice imputation or both, or use mode, or actually not use at all. As you can see here, as the user applies M estimator or mice imputation, we get a different number of GRBs because of the pre-processing, and then we divide the set into training and test sets and do feature selection, and transfer it to our superlearner ensemble method and find the best subset of models to find our specificity and sensitivity. Similarly, we did the same thing with optical features. Here we got around 171 GRBs, and our best performance was at AUC 0.841 and TPR at 0.741. Similarly, the methodology here is similar to the X-ray, and we outsourced it, open sourced it using a web app. There are 2 web apps, one regressor and another classifier, where, as I told while explaining the methodology, the user inputs GR.
I cannot hear you, Milind. I don't know if it is only my problem.
Me neither. I cannot hear.
Okay, I think it's connection I got connection issue, I guess. I got disconnected.
So for using AI to estimate the redshift, but it seems that, for example, JRFT has so many like little red dots that are not yet well understood. So I worry about whether you can train the machine.
I cannot hear you. It's not audible.
Can you repeat the question with a microphone, because we could not hear you? Sorry. What are you worried about? We cannot hear you the question. I'm sorry.
I think in the meeting room they cannot hear us.
Maybe in the chat we can write.
redshift that applies.
So we cannot hear the question.
But the method that they are doing is a machine trying to understand some relation between
Gli è spaccato il microfono. Non gli funziona il microfono, ragazzi.
We cannot hear the
Il
question.
microfono, ragazzo. Ha tolto lo screen, ha tolto.
Milind, can you put back the screen?
Yes, sir.
I think that would be a major discovery.
Yeah, because you got frozen. Just go back to the presentation. Last slide you had, right?
Since there are some issues, we will move to the next presentation. Sorry, but we are late.
Okay, fine.
Maybe let's ask one you just to make a statement.
Okay, Wang, you make a statement.
a statement.
That's about the
About to inferring a redshift, I think that's the most important question of using GRBs. But from the current data, I saw the results. The result has a very big scattering. So I think it's not a very easy job, but they are having a very good starting.
Well, but the thing is that the scatter that you see that is large is because we also use Monte Carlo simulations to rerun our analysis, taking not only the central value, the best fit value of the parameter, but also the one sigma range. So we were practically obtaining the value of the prediction for each variable between the minimum and maximum values within one sigma, and we repeated this procedure 100 times. Then we averaged on this prediction, and then we extracted the minimum and maximum of the redshift. That's why it's very realistic, even maybe pessimistic estimate, but this is something that you don't find in the literature, because usually they provide the error estimate, but not the estimation, but not the error that it is provided by the uncertainty of each variable.
Okay, thank you very much for this discussion. I'm sorry, but we are a little bit late, for half an hour late from the schedule. So we thank all the speakers of this morning, and we move to the next presentation, which is by Rahim Moradi. So Rahim, can you please share your screen?
Yes, I think it's deactivated. The organizer should authorize me. Okay. Okay, now I can share.
No, yes. Rahim, can you hear me?
Yes, yes.
A little bit change on your presentation, because at 11:15 Italian time, Professor Rufini has to make a presentation. So let's do this. 25 minutes you speak, then we break, then we continue after that, if you agree, okay?
Okay,
Just this time Professor Rufini will speak, okay?
Okay, so let me...
Minutes before.
Can you see my screen now?
Yes, we can.
So it's full screen, all the... Okay, if you can hear me, I can start.
And I will let you know like 2 minutes before 11:15. Okay.
Okay. Good morning there and good afternoon here for people in Beijing. So today I will be, for the next 25 minutes, I will be talking about the analytic framework for neutron star critical mass across equation of state of model in gamma ray burst. The approach is to use the inner engine of the GRBs like magnetars and neutron star rather than black holes, and I will discuss where and when and under which condition we should use a black hole inner engine, and also regarding to the previous talk, we expect in some cases to have a black hole central engine. So I will shortly talk about gamma ray burst, then I will talk about evidence of neutron stars or black hole in the light curve. I introduced multipolar emission to solve many observational problems that we have either in the phenomenological relation like Dynoti relation and also in the observation of afterglows. I will use Swift XRT observation, then I will go to explain within this model the Dynoti relation, then introducing constraint of the equation of state by black hole physics, and also toward more complex model of afterglow eccentricity and all this strange and physical thing that I can add to the system to make it more physical. So these are related paper we have been publishing with Ikranat group, also in IHEP. Many work, also many, some of the work are under the review, some are published and some have been submitted recently. So some results are preliminary and some are already published. So for those who don't know, we have this gamma ray burst. So in this talk, I will mainly focus on short gamma ray bursts when we have two neutron star collapsing either to massive neutron star or to black hole. And this is for the next talk that Chen-Wei will talk about new subclass of short long gamma ray bursts like the Centauros, that in the head they are long, in the tail they are short, so and vice versa. So how to recognize them? Chen-Wei will talk about this using JCAM data, Swift data, and some way to identify this new subclass. In the theory that we have been developed for a long time in Ikranat groups for long GRBs, the neutron star play a crucial role, but also the black hole play a crucial role. So talking about neutron star is much related to all model of the GRBs. So since I don't have time, I will go fast on these slides to go to the point. The point in the BDHN is that the prompt is in the most energetic GRBs is explained by black hole, the afterglow explained by the kind of magnetar or neoborn neutron star is better to call it. And for the early phase, we have this black hole physics, magnetic field around the black hole, then it will induce some electromagnetic effective charge. This effective charge will produce some plasma around the black hole. They will be expanded till the moment that they are transparent, and then they will radiate the MeV. And as you can see, after that, they cannot reach to the afterglow. And for the afterglow, we need another mechanism that is the role that neutron star comes in and magnetar comes in many models. So there are many phenomenological relations that can be explained by any model that we can propose. for, as I mentioned, the most important one to explain today is diagonal relation that we have this pleasure to have herself, Dainoti, here to more discuss about this thing, this model that we have. So I go directly to the model that we have. We want to present here. We mainly talk about short GRBs here and the afterglow emission. And we mainly talk about supermassive neutron star, which later they will collapse to black hole. And I will explain you how. So first, how to explain all this with the magnetar. We know that the magnetar and dipolar field, classical dipolar field, they predict a plateau, also the late afterglow with the power law index of -2. But we know that from many observations, as you can see in the panel, late afterglow, although we have many plateau, late afterglow, they don't follow -2 in many cases, and the majority are around 1.5, 1.3. So we need to know why, if this classical dipolar field doesn't work for explaining the afterglow, what can produce this. So we proposed something that this can be, last year we proposed a model that can be due to the existence of a dipole, quadrupole, hexapole, and a higher multiple in the afterglow. And you can see they can predict different late afterglow indices. So for the dipole -2, for the quadrupole -1.5, and as you can see, there are a spectrum of the, not the spectrum, but there are acceptable values for explaining the afterglow. So the mechanism for fitting, we followed these general equations. We solved the integrals for including many higher order multiple for fitting the afterglow, and we found that in all of them, using correct test for fitting, also many different methods, including Monte Carlo, to show which in GRB physics, in the GRB afterglow, which one is dominant. And in almost all of them, we found that a single dominant multiple, like in some GRB quadrupole, in some GRB hexapole, in some GRB dipole, works well. So this is the first result that we had, that multiples, higher order multiple with high mathematically and physically predict the afterglow of the GRBs. So, and also we have the evidence from other methods of the higher order multiples in the literature for XRBs, SGRs, and other sources, and that can prove that the presence of the higher order is necessary. Also, in many other sources, fast radio where superluminous supernova, all of them predict this presentation of magnetar. But the first thing to solve with this mechanism is the diagonal relation and magnetar model. As you saw in the 2D diagonal relation, the problem is that dipole can explain, but dipole cannot explain the afterglow power law index. So what we have been doing, we implemented in this idea, and we show that by considering that general formula for the multipolar electromagnetic radiation, we have this L0 I omega 0 squared divided by 2L tau. And we got the universal thing that no matter of which multiple is dominated, always this can lead to the famous dynamic relation. And but the strange thing about this, that in the same time that can explain the dynamic relation, 2D dynamic relation, it can predict and explain the late afterglow emission. Also, with platinum data sample, as you can see here, also when we fit this platinum data sample and we check as the 1 millisecond period as the lower limit for the magnetar, also 10 kilometer radius, mass 1.4 solar masses, we can get that the upper limit statistically still leads to L, which is related to higher order multiple, still more than 1. So also in this case, it proposed that we need more multiple to explain this relation. But there are some caveats that we are currently working on that for sure we consider is not from external shock or other models, it's from the multipolar radiation. So we didn't consider the wind effect, plasma effect that can modify a bit. Also, we didn't consider the jet geometry from because for the dynamic relation, we use the isotropic one. And also, we didn't consider that it's from black hole. So these are some caveats of this model, but not a big problem of this. And we have shown, for example, for the wind effect, although there are not rigid theoretical model that how multipolar can give its energy to wind, but some evidence showed that it doesn't change the relation too much. So for the main conclusion of this is that the magnetar with multiple can, in let's say more than 90%, can unify GRB afterglow behavior. But we agree that maybe in some cases black hole can explain them. But also that one needs to take care of everything like the prediction of the afterglow, how to have this all observational values simultaneously valid. Next work that we have just submitted is the probing neutron star equation study within this model. So in some cases, when we have this decay, it's abrupt decay, it's like vertical decay. So that's the way that we consider it's the collapse from the supramassive neutron magnetar neutron star to a black hole. So how to solve this? I will tell you in the next slide that how we can use this. We can use this to put constraint on the equation of state of and also maximum mass of the neutron star, which can we can put constraint on radius, also phase transition, or many of these physical phenomena, which is a very important thing, even in the study of the evolution of the neutron star itself, which I explain later why equation of states is more important than what we see only in this slide. So the idea is that we have neutron star merger, the supramassive neutron star, then X-ray plateau, then black hole collapse, so sudden decay. For this one, we have searched for this sudden collapse. There are lots of GRB, but with clean data and with high quality data, 10 reliable one. So we fitted them by this luminosity of the multipolar radiation, and we found that before the collapse, before the sudden collapse, they are well fitted by the multipolar electromagnetic radiation from the magnetar. And after that, we consider it as a black hole collapse. So what's the idea? Before collapse, to the moment of the collapse to the black hole, we consider it is evolving by the multipolar spin down, so we can track the spin. At the moment of the collapse, we have the massive neutron star and the black hole. So we were lucky in group in Ixtranet that we have both a neutron star and black hole mass developed in that group, one 50 years ago by Christodoulou, Ruffini, and separate by Hawking, and one 2015 by Cipolletta, who was another student in our group working with Rueda, Ruffini, and other collaborators. They proposed a very beautiful neutron star mass, critical mass, but unfortunately for only 3 equation of state, which I after this I will talk to Professor Ruffini and also Jorge to see how we can extend this mass to more equation of state, which is very precious in my opinion. So at that moment, we consider mass of black hole is more than this critical mass. Then we have 2 alpha and m, but 2 equation, and also we demand that the energy after the collapse is paid by the black hole. Before that is paid by the neutron star. So all this together, we solve the equation. We find which equation of state works well. As you can see, the best equation of state is the one that fits the delta P the best. Delta P is the P obtained from the neutron star during the multipolar radiation at the moment of collapse, and the one obtained from the collapse of neutron star to black hole. So, as we can see, that it shows that the best equation of state that fits this is the not soft one, not stiff one, is the medium one, is GM1 with 2.4 solar masses. And also, if we consider the quality of data in some GRVs, like here, the final solution is that TOV of this mass is 2.3 plus minus 0.1, which is well fitted with the data obtained from many other methods, either from the numerical methods, either from the gravitational wave methods, from other methods. So it's a very well known number that we have obtained separately and using new novel methods here. So the point is that it has good result. This mass is 2.3 plus minus 0.1 solar mass, but we are expanding the sample of GRB to, you can see like Einstein probe or other data. Also, we include more a bit like because we didn't consider accretion physics, we didn't consider efficiency, we didn't consider it's many equation of states. So when we consider this, which we expect the same result, but we are currently solving with more full GR simulation obtained from the numerical simulation. So that's already good result, but we have been going forward and still working on other aspects. Recently, one of our the paper got published in APJ, also in the collaboration with Ixtranet and some others. That what happened if we consider the full eccentricity? This was work that we have been doing with Ixtranet group for a long time. And it's very interesting that for the first step, when we consider eccentricity and for the compressible neutron star and polytropic equation of state, which we need to modify this polytropic equation of state with our formalism, but this is the first approximation. We could get the famous X-ray flare based on this formalism. So it's very interesting that it's for the first time it gives very concrete result, very concrete prediction that X-ray flare can be due to this sudden spin up, which happens because of the compressible nature of neutron star. and the equation of states, considering this not soft, not very stiff. And when we consider all of them together, all the possible physical things that we can consider, like the different electromagnetic multipolar radiation, also gravitational wave radiation, we can explain this very beautiful behavior of the X-ray flare that we see in the early X-ray afterglow. Also, as a toy model, we checked for the compressible model that how gravitational wave and dipole or quadrupole can be seen during this GRB afterglow of GRB evolution. And in some cases, first the gravitational wave we expect, then the electromagnetic, and in other cases when the quadrupole are dominant, we first expect electromagnetic radiation, then gravitational wave. And with this toy model for the next generation, it shows that the next generation of gravitational wave emission, we expect to observe at least some gravitational wave emission from this eccentricity and the release of gravitational binding energy. So the conclusion is that yes, multipolar magnetic field is successfully explaining afterglow of GRBs. Also, eccentricity is needed. A more realistic solution, we should combine more realistic equation of state that we obtain from different methods, then consider gravitational wave, dipole, quadrupole. Also, numerical solutions are essential, or more comprehensive mass for neutron star to extend this work of Cipolletta or Ruffini. Also, very interesting that proper equation of state together with this eccentricity explains the early X-ray flare, mysterious early X-ray flare very clearly and very beautifully. And at the end, I should say that yes, many people use this collapsar model, and black hole is necessary there, but there are two possibilities that one, this black hole can behave like magnetar, as was a bit explained by the previous talks, but it also strongly suggests that long GRB's progenitor are binary system like the BDHN model. Thank you.
May I ask a question?
Yes, please.
Thank you so much for your very nice talk and comprehensive overview. But I would like to ask you whether you have considered also, with data in which we also consider the losses.
I didn't hear you well.
Yes. So, are you also planning to consider radiative losses? Because you just use
Exactly, yes.
this formula, yes, of the perfect dipole, but we also, for example, investigated the magnetar model with Stratta, myself, and other collaborators, in which we added also the term, the contribution from losses, and this changed a little bit the fitting.
Yes, I agree with this. But for the first time, we first intended to explain how we can explain this diversity in the afterglow temporal index, power law index. When we were successful in explaining this, so now we are tackling other problems to implement more about efficiency, about opening angle, about different physical phenomena, different physical coefficients that can alter our results.
And also, I would like to point out a paper from Li Liang in 2018 that he was actually studying the magnetar versus black hole taking isotropic emission and the GRBs, and the fraction can be different whether or not you consider collimated or isotropic. So there are several parameters that when you change them, also results will change somehow. Degeneracy. So we need to pay attention to this issue as well.
Yes, sure. Yes, we are doing this. We are in this stage now.
Thanks.
Can I ask another question?
Yes, sure.
Okay, thank you very much for a nice talk. I was wondering, maybe I lost it, when you study the transition from neutron star to black hole, do you consider accretion rate? Because in
No.
order to have...
Yes, since we consider this is a neutron star merger, we consider accretion rate to be low, but yes, in principle we can consider this part also. But in this case, in light of the merging and the final neutron star mass, we consider accretion rate to be lower in the comparing to in the collapsar or other cases.
Yes, so when we already switched to black hole, does the luminosity of this black hole require it to accrete, or we have just a residual luminosity from the shocks?
Yeah, I in one slide I showed you, in this stage we only we only answer this question, that if this energetic we observe is paid by the black hole, what will happen? So we don't care, we don't answer the question how it is paid. This is the point. So we don't answer this. It can be from I don't know, Blanford's-like mechanism. It can be from different mechanisms. So we don't answer this. So just only if the energetic is enough to put constraint or no.
Okay. I was wondering if you have some hypothesis on this, but thank you very much.
Yeah, because this is the part that we have been working a lot with the Ikranat group about how to extract energy from black holes. So in different scenarios, we have been working, but when it comes to X-ray, it's still not very clear, to be honest.
Thank you very much.
I think they have problem in the meeting room too. They have problem with the speaker. I think Chenwei, you can start. They can hear us, but they cannot talk. Chenwei, are you there?
Yes, can you hear me?
So let me stop sharing.
But it seems that I don't have the. Can you hear me?
Okay, let me tell you. Tell them to authorize you. Yes, they are. Afraid if they authorize you, yes, we can hear you. If they authorize you, you need to restart the program, reopen it.
Yes,
But let's see how.
I click it first.
Just okay, Raim, there is a question for you. So meantime, we prepare share the screen. Okay, so Carlos wants to ask you a question.
Yes. Hello, Rahim. Nice to hear from you. Long time no see. This is Carlos Arguelles. So I wanted just to ask you if you can comment a bit more about the relation of the studies you have been thinking regarding dark matter in your system. Can you hear me?
That's a good question because we had a collaborator here. Can you hear me?
Adesso they can hear us, but we cannot hear you.
Now they cannot hear us.
Yes, but now we cannot hear them.
Can you hear?
Yes.
Yeah, about dark matter, yes. In principle, we can implement. As far as I remember, we had a collaborator here last year. We were studying this problem together. He moved to the part of dark matter to check with him that in which level he is, because he was more interested in constraining on dark matter and how dark matter can uh, the, add more effect on this problem. I don't know if you can hear me or no. Now I cannot hear you. Chenwei, can you share your screen?
No, I still cannot share my screen. I don't have the permission from the software.
Let me.
I just quit and
Yeah, wait. Did they authorize you?
no. Should I quit again?
No. Wait if they authorize you first. Apparently, they have a problem with the speaker, so with the microphone there. So I think we should come back after the coffee break. They have a coffee break now. They are
Okay.
trying to solve this problem.
Okay, thanks.
You're welcome.
Okay, now. Okay, now we can see your screen and the presentation. Now not.
Before that, we received a reply. Right. You told me that maybe you told me already.
Yeah, I corrected. Yeah.
Okay.
Yeah.
Because before that, we need like an authorization of the knowledge coming to your
No, without the microphone. As I said, yes, they can hear. You can hear me now. Yes, I want to ask you to start. 陈伟，
Yes, I can hear.
你可以开始了。
Oh, okay. How many time do I have?
I don't know how much time because the chairman is not in this room.
Hello, can you see my screen?
Yes.
Okay, then I will start. Good morning and good afternoon. I'm Chen Wei Wang from GCAM team. It's my great honor to be given a chance to share our works in this meeting. This work is supervised by Professor Shaolin Xiong and Rahim Maradi. As we all know about GRB, so I won't talk about this. Actually, in the past 5 year studies of GRBs, we found that some gamma ray bursts have a precursor, and usually, if a duration of the burst is longer, and the duration of the precursor is also will be longer, and the quiescent time between the precursor and the main emission is also longer. So this is the one important. Our work is very associated with the precursor shape. A well-known classification of GRB from the morphology is the long burst and the short burst based on the kinetic. And generally speaking, we think the for the long GRBs, they mainly originate from the core collapse from the massive star. But for the short GRB, they are mainly from the merger of compact stars. This main motivation is free fall time scale. But recently, more observations suggest that some long GRB bursts may also originate from merger. Previously, people tend to expand them as short hard GRB with soft long extended emission. But recently there are two other events named 230307A and 211211A. These two bursts they have a distinct long duration of the main emission. So to classify them from the typical short long duration short GRB, we call them the type 1L GRB. The L means long. Among the observation and research of 07A, GCAM played a very important role. GCAM first reported that this is an extremely bright burst, and then leading a global observation companion to this event. And both of them didn't suffer from the data saturation, and both GCAM B and GCAM C has a high time resolution as high as 0.1 microsecond. There is here is an advertisement that based on the high time resolution GCAM data, we recently found a high significance kilohertz predictable signal in this burst, which is already accepted by Nature Astronomy, will be published recently. So we also welcome researchers come to use GCAM, HMT, and also Swarm GRM data. In fact, the GRB observation has developed a well-defined observational procedure. For most GRB, the companion will start with inflat trigger of a wide field of view monitor, and first we can always got the light curve. Some of them we can got the spectrum, and some of them, if we have a good localization, we can also got the afterglow in the X-ray and optical. Actually, if we want to get more information, the more exposure time in multi-wavelength are needed. So we got the less sample size. The limited exposure time, if the exposure time is limited, so we should priority for the peculiar events. In some case, the cost may even increase as the localization is very poor. So maybe we can use the IPN or the soft X-ray tailed observation to find the localization, and then we can perform the follow-up observation. But it's necessary to tell the follow-up instruments that is really important, and so they deserve to spend a lot of time on them. So it's just like gambling. If you tell them this is important, but they didn't find anything, and they won't help you to follow up this again. For 07A, it's just this case. There are a lot of there are a lot of works to try to get the precise localization and a lot of tailed observation by XRT, and even we use the GWST was performing an observation after 1 month later than the trigger. So people are actually initially attracted by its high brightness, but without realizing its long duration short GRB. So if this burst is not the second brightest burst, people still spend so much time on the follow-up observation of this event. This situation is also the same for the 211211A, as that burst is also bright. But we can say that not all the long duration short bursts have a very high brightness. So if we want to increase the sample size of the long short GRBs, we need to get some method to identify them quickly from the light curve and also the spectrum. So then it can be sufficient motivation to conduct the joint observation. Follow the idea, we try to find some common features from the light curve by us, not by the machine learning at these steps. It seems that both the 07A and the 11A has a precursor, a main emission, and followed by a deep structures. We are not the only team notice that this thing. So, but a problem is that whether the first peak of the is the precursor in O7A is not true, as we think is not, there's no quiescent time in the burst. With some detailed analysis, we've confirmed that if this burst is far away, more far away, and a quiescent period will exist. And note that the quiescent time of this burst is very short, but the burst is long. So that means it's not follow the relation between the quiescent time and the duration of the burst, as we know. So when we plot these two bursts on the t waiting time and t90, we found yes, it's indeed diverge from the relation. So here we conclude a 3-episode burst pattern for this burst, that it should have a precursor followed by the short quiescent time, and it should have long duration main emission and possible main extended emission. Following this burst pattern, especially the first short quiescent time, we indeed we conduct a manual search for the type 1 outburst in GBM archive data. We indeed found one, but only one candidate in our first search is named 170228, and it follows the 3-episode burst pattern strictly. And importantly, we found all the properties of the prompt emission are consistent with the merger origin. Unfortunately, such a burst is very weak and ordinary looking, so it didn't gain enough attention. So there's no public available follow-up observation for this burst. In fact, this is also the situation for most GRB. After that burst, we also developed an automatic identification program and found 2 more bursts in the GBM data. They all localized location in the they all have a short waiting time and long t90, and then we found they share the same properties of the prompt emission and consistent with the merger origin. So we think the burst pattern is probably an indeed good way to identify the type 1 LGRB, the long duration merger origin GRB quickly. And as the BA of many instruments, one of the key aim of the work is to provide a good reference to rapidly identifying this burst and then coordinate follow-up observation. Recently, we indeed found one burst, 250521D, and we found this burst have followed the burst pattern and is also localized in the type 1 region of in MRT. So we indeed we quickly perform some follow-up observation. We are pleased to see that the concept of type 1 LGRB has also accepted by some other research. Some of them try to using machine learning to identify this event, to identify the events with the same burst pattern, and they got more events. Also, they found there is a precursor identified in the GRB 060614. We used to say in the previous we used to say the burst is ordinary a typical short GRB with extended emission. Now it's with their analysis, they think they suggest is indeed follow the burst pattern of type 1 GRB. I'm not a foundationalism, so I think the evolution of the type 1 LGRB is good. It will help us to understand the nature of this kind of events. Importantly, there are research by machine learning. Their search for by machine learning have confirmed that the precursor is a crucial crucial role in the type 1 GRBs. With some comparative analysis of the precursor in the 07A and the 11A, we found all these precursors share a high energy budget and short time scale and the structured light curve features. So all these features can help provide a constraint on the progenitor dissipative process and radiation mechanism. And for this, interesting is for these two particular bursts, almost all type of progenitor models can provide some reasonable explanation, including new star, and neutron star with black hole, and neutron star with with white dwarf, and even neutron star with black hole. So with the size limited sample, we cannot make a final conclusion that how to produce such kind of burst. So we think the conclusion should still rely on the gravitational wave detection, especially which whether the gravitational wave or the precursor comes first. It will help us to answer which model and which progenitor and how the energy is dissipated. Except from the burst pattern of type 1L, I mean from the pattern itself, what can we get from get more? I got two things we can discuss. The first is that the T90 for the double Gaussian. As we know, there are a lot of classification criteria are proposed to replace the T90, but some of them are such as MVT, but some of them is not as the cluster of type 1 and type 2 are not as separate as T90, but some of them need very a lot of information such as host galaxy or the redshift. So this leads to it's hard to identify them quickly from the prompt emission. So T90 is still the most effective and widely used criterion. However, as we see, the long burst is usually associated with type 2, and the short burst usually associated with type 1 is because we use a 2 Gaussian function to fit the T90 distribution. However, we find in the type 1 LGRB, if we think all these candidate events are true merger origin, then we can find the number of type 1 LGRB number is much higher than the predictions of the Gaussian distribution. That means...
Sorry to interrupt. Could you please a little bit speed up because we are a little bit late on time?
Okay. This is only 2 pages later. So that means if a burst, if the Gaussian distribution predicts that we only have 1 or 2 events at this duration, but now we have 5, that means probably the distribution of T90 is not is not truly of 2 Gaussian, maybe 3 Gaussians or 4 Gaussians. So I think the measurement of the intermediate duration burst to find the ratio of type 2 and type 1 of them is very important topic in the future. And another is we find since this burst, they all follow the same burst pattern, and surprisingly, they all located in the same, they share the same parameters in these relations. So that means the similar GRBs, the similar GRBs may have the similar physical process or similar origins. That's all of my presentation, and I won't read this summary. Thank you.
Okay, thank you. There is a question from Wang Yu.
Thank you, Chen Wei. Your talk is very nice, clear, and informative. I have a simple question that you showed the precursor has thermal, yes?
Yes, the precursor is quantithermal. Let me find this pictures.
So my
Yes.
question is, did you compare, because you have found a new class of GRB, and you have a first short thermal precursor, then continued by a long period of emission. But if you look at the soft gamma ray repeaters, also they have a very short initial thermal spike, then followed by long time emission. So can there be something similar from the mechanism, the emission mechanism between these two?
Yes, it's very good questions. Actually, if there is, I think such a scenario is possible that there is a magnetogiant flare in our galaxy, and we cannot look at this location, but we only see the first initial soft thermal initial spike and the long pause after that. So yes, I will try to compare them more. I think is indeed a problem.
Okay, thank you very much. Thanks, Rahim, and thanks for Chen for all the presentations. So now we move to the next presentation. Fateme, can you please share your screen?
I will give you the permission. Wait.
So 1 second, we will give you the permission.
Hello, everyone. Can you hear me? Okay.
I give it to you the permission.
Okay. Can you see my screen?
Yes, we do.
Okay, and can you hear me?
Yes, can you hear us? We can hear you.
Okay. So let's start. My name is Fatema Rastegarnia, and I am the researcher in ACRANET. And today I'm going to talk about I want to introduce the FNet for spectral classification. And we have done this research in collaboration with Dr. Moradi, Dr. Mirtorabi, Dr. Wang Yu, and Dr. Wafai Sadr. First, I'm going to talk about the motivation and give a brief introduction, and then I go through the data and its challenges that we have faced with, and I'm going to brief introduction to what is the convolutional neural network and what our neural network is, I mean the FNet, and I will discuss about the results and the future perspective that we will face. Over the past decades, astronomy has been undergoing a true data revolution with next generation telescope and highly sensitive detector. We now have access to part of the universe that were completely hidden just a few years ago. But collecting data is only the beginning. I mean, turning the raw data into scientific insight is an entirely different challenge. Modern telescopes are generating more data than we can possibly process manually. This is where machine learning and automated algorithm come in, and they help us to find a handful and of interesting signals in the ocean of observations. For example, we can see the Vera C. Rubin Observatory, known as LSST, is set to survey the Saturn sky every few nights over a 10-year span. And what is the result? A time-lapse movie of the dynamic universe, and it is expected to produce around 20 terabytes of data per night, and adding up to 60 petabyte by the end of its mission. And also another example is the Square Kilometers Array, SKA, which is located in South Africa and Australia, and will be the largest radio telescope ever built. And it's projected to generate over 600 petabytes of data per year. And processing that data in real time will depend heavily on artificial intelligence. And the projects like Gaia and Euclid and Pan are also contributing petabytes high resolution data on stars, galaxies, and cosmic structure. Each night they deliver terabytes of new observation, and that must be processed, labeled, and classified. Here you can see what the data revolution looks like in practice. These are some of the major telescope and survey operating today, and I have mentioned SKA, Rubin, and Gaia, but they are just a part of a much bigger picture. And this table highlights a range of major astronomical projects from Euclid, which is focused on dark energy, to LAMOST, which is building a massive stellar spectral catalog, and FAST, which is scanning the sky for pulsars and hydrogen signals. So some generates petabytes per year, and other deliver the gigabytes of high precision data daily. But together they present a shift. Astronomy has become a data intensive science. And what's clear from this table is that the astronomy today isn't just about collecting lights. It's about managing and understanding data on an industrial scale. And to keep up, we need machine learning, and not just as a helpful tool, but as a critical method for discovery. Since 2023, the number of methods for classifying astrophysical objects has more than doubled, from about 10 to over 20 distinct techniques. And this range from classical machine learning models like random forest and support vector machine to advanced deep learning approaches, including convolutional neural network and transformers. And importantly, these methods are applied across different types of data, and not just a spectra, but also photometry and time series observation and images. And recently, a hybrid model and unsupervised learning are becoming increasingly popular to handle the complexity and volume of the data. And we can see here the template matching, which is a classical method for redshift estimation and classification, and which compare the spectral templates. And you have to go spectrum pixel by pixel, which just doesn't scale well in the era of the big data. It is accurate, but it costs a lot and it's very time consuming. To understand our approach, it is important to first look at the data set we are working with. We are working with the data release 17 of Sloan Digital Sky Survey, for short SDSS DR17, which is an incredibly rich resource, and it includes over 623 terabytes of spectroscopic data stored on the SDSS Science Archive server. And in total, the release contains around 1.5 million spectra, but our focus is on the subset from the EBOS catalog, and which is a stand for Extended Baryon Oscillation Spectroscopic Survey. This project is a major spectroscopic survey that is part of SDSS-4, and its goal is to improve our understanding of a large-scale structure of the universe by precisely measuring the distribution of galaxies and quasars at high redshift. And this EBOS DR17 dataset alone gives us about 1.4 million high-quality spectra, which the foundation of our current research. And these spectra were collected using a 2.5 meter telescope at Apuchi Point Observatory, which is equipped with 500 fiber per spectrograph and 2K CCDs. And the wavelength coverage is from 361 to 1014 nanometers. Ensuring the data reliability is essential for effective model training. Therefore, we applied some important criteria and filtering criteria to construct a high confidence data set. First, we kept only the spectra with the highest redshift confidence, which is announced in our catalog as a Z-conf equal to 3, and it means we use the high confidence redshift. And the second filter is for broad absorption line quasars that we required, which is announced in our catalog as a BAL probability greater or equal to 0.9 for reliable BAL quasar detection. And we also include only visually inspected spectra, because visually inspected spectra is the most reliable reported from the for redshift or classification. And we're using the condition redshift visually inspected greater than 0, and we put we want to be sure that is quasar final, which is announced with quasar equal to 1, to be sure that our data set consists of the quasar. For the first project that we use the FNet for estimating the redshift of the quasars, because our project first was for the estimation of the redshift. And you can see in this histogram the confidence subset on the pink column. Finally, after putting these criteria, you can see our data set, and obviously the majority of our data set is allocated to quasars and stars, and so we have the imbalanced problem in our data set that I will explain how to solve this imbalance later. It is important to clarify this point that these criteria we used to build our training and test set did not impose any constraint on the signal to noise ratio, and In other words, we didn't filter the data based on the signal to noise ratio threshold. Instead, we kept the full range of signal to noise ratio values that naturally occur in the data set. As shown here in the histogram, you can see that you can see the distribution of the signal to noise doesn't change during the putting the criteria, and this approach helps ensure the model remains robust and perform well even on the noisy and low signal to noise ratio spectra, which are common in the real survey. And to enable the deep learning networks to process spectroscopic data efficiently, the data preprocessing plays a critical role, both in performance and for model reliability. And this involves several steps, starting with data cleaning and manipulation. And at this stage, we may remove certain part of the data or make minor adjustments in order to ensure that remains in high quality and consistent and representative. So we apply the normalization, which helps bring all the features on a similar scale. This is especially important when dealing with a physical measurement like flux, which can vary dramatically between objects, and without normalization, some features might dominate the learning process just because of their scales. We also perform vectorization since each spectrum can be thought as a one-dimensional signal, essentially a vector of a flux value over the wavelength. We need to convert each observation into a numerical format that our network can interpret. In our case, each spectrum from DR16 and DR17 dataset is interpolated and extrapolated to a one-dimensional vector with 4,618 flux points, and evenly spaced in logarithmic wavelength space. Across our wavelength space from 360 to 1040 nanometers. And this uniform representation is important for training consistency. But because observed flux can still vary significantly, we therefore apply zero mean and unit norm normalization, and this improves numerical stability and speed of the convergence during the training. Here you can see the effect of normalization. It didn't change the prominent feature. It just scale all spectrum and it increased the speed of the training process. To understand how our model works, let's just first take a very quick step back and talk about the convolutional neural network, for short CNN, which is one of the most powerful and widely used tools in deep learning. And you can see it contains of some important layers. The most important layer and the heart of the architecture is the convolutional layer, and it means that there is a small sliding window or kernel. Some people say it kernel or filter, which moves across the input and detected the local features for spectra. This could mean recognizing the emission or absorption line, and after that convolutional layer, we have the activation function. which is a non-linear function like ReLU, which pick the positive volume of the how can I say, the pixels on the features that convolution layer produce, and it helps us to introduce the more complexity and make the network capable of modeling the nonlinear relationship. After that, we use the pooling layer. In this project, we have used the max pool. This layer reduces the dimensionality of the data by summarizing the neighboring values, and this helps the model generalize and reduce computation. And after that, we flattened the extracted feature and send them to the fully connected layer, and this is where the actual classification happens, and mapping the learned feature from the output, in this case classes or redshift estimation. I'm not gonna go through through the details, but here I want to focus on the loss function, which is and calculate the loss and optimization function, the method of optimizer that we have used. I just want to notice here that we use a cross entropy loss function for classification and mean square error for regression task. So what exactly does the optimizer do in a neural network? In simple terms, the optimizer is the engine that drives learning. It updates the model's weight to minimize the loss function, which measure how far the model is the model's prediction are from the true label. After each batch of data, the network compute a loss value. The optimizer then uses the method called gradient descent to calculate how each weight in the model contributed to that error. And it then adjusts the weights slightly and in the direction that reduce the loss. And this process is repeated over many epochs and gradually improving the model's prediction. And now you can imagine that the choice of optimizer matters a lot. In our work, we use the Adam W for classification and Adam for regression task, and we have the test on around 40,000 spectra of data release 17 to compare this optimizer function. And you can see the Adam W for classification is much better, and it converge faster than Adam or root mean square propagation or other grad or stochastic gradient descent. So I choose the Adam W for classification. Let me walk through the learning process. How the neural network actually learn from the data. It's all started with an input. For example, a spectrum from the SCSS survey. The model perform a feed-forward processing and applying layers of computations like convolution, activation, pooling, and then produce a prediction, and such as probability that this object is a quasar or stars or galaxies, or maybe estimating the redshift. Then we compare this prediction with a true label using a loss function. And in our case, as I mentioned, for classification, we used a cross entropy, and for regression, we used a root mean square error. And this loss value tells us how wrong the prediction was. The next step is backpropagation, where the model compute the gradient, essentially how much each parameter contributed to that error. These gradients are passed to the optimizer, and which then update the model's internal weight. And the goal is to adjust the parameter in a way that the next prediction will be a little more accurate. And this process repeats over many epochs, which the model gradually improving as it sees more data and correct itself. And over time, the loss decreases and the model become better generalizing and classify new and unseen spectra correctly. Up to this point, I've talked about the standard convolutional neural network, the stack of layers where each one transforms the data and passes it to the next layer. But there is a problem that arises when the network get too deep. They start to underperform. You would see that our neural network is a very deep neural network with 24 convolutional layer, and maybe you think that adding more layer should make a model more powerful, but in practice, very deep network can become harder to train, and they suffer from the issue like vanishing gradient or degradation, where adding layer actually make performance worse. That's why we used this wonderful network, which call it ResNet or residual network, and this is one of the most important breakthrough in deep learning. What is a ResNet? ResNet introduced a concept called residual learning. Instead of learning a full transformation from input X, each block learns a small residual function f of x and add the original input back in f of x plus x, and this is called a skip connection or shortcut. And you can think if it is like if the model doesn't need to learn anything new at that layer, it can simply skip over it, and this helps the network avoid overfitting or instability in deep architecture. So residual connection allow the model to learn faster and preserve important feature across the layer. Now the question is, what is exactly the FNet and how does it work? FNet is a deep one-dimensional convolutional neural network with ResNet architecture designed specifically to estimate the redshift of quasars for spectral flux. Therefore, FNet is designed to find the higher order feature in the input observed flux. The optimized convolutional layer transforms the feature of visually inspected redshift in the output layer. And in this view, the neural network model is only a mathematical function that maps an input, observed flux, to the desired output, redshift. Our net is similar to QuasarNet, which is also a CNN-based network, which is applied on SDSS catalog as a artificial intelligence application for redshift estimation and classification. However, the design thinking is completely different. QuasarNet imitate the traditional procedure of redshift estimation, namely first identifying the prominent line and then inferring the redshift from the detected line. In our CNN, instead, the net is trained to discover the hidden pattern by itself and without given any external information, including lines or other extra information. This hidden pattern can be emission line or absorption line present in the spectral, or maybe the global shift pattern or specific pattern in different redshift or pattern related to the correlation of fluxes at different wavelengths. These two approaches of thought lead to different results and different range of application. To find more abstract pattern and to have more accurate prediction, FNet is deepened by incorporating 24 convolutional layers in its architecture. From our current knowledge of neural network, each layer of the neural network extracts different levels of feature information, and the deeper is the network, the more information will be extracted. This strategy strengthened the capability of FNet to generalize its prediction of a spectra with a wide range of signal-to-noise ratio, as well as a spectra without prominent emission line. Here we can see the architecture of FNet. We have 3 convolutional layers stacked in the ResNet block, and also we have 8 residual ResNet blocks linking together, and so in FNet, each convolutional layer has 32 or 64 filters or channels sliding along each row of flux to extract the prominent feature, which are passed to the ReLU function and rectified linear unit activation function, and that allow the model to access nonlinear modes if they are needed. The convolutional layers have the different size of kernels, from small filters to medium kernel size to 15, to medium size 200, and the large size to equal to 500, and are stacked as a residual block and duplicated in series, and forming a deep network of in total 24 convolutional layers, and shortcuts are applied between each 2 residual blocks. And it should be pointed out that the convolutional layers are initialized with a He-normal initializer. And finally, we have the fully connected layer to extract the feature to the output redshift. However, the deep network always encounter with a problem of gradient vanishing and exploding, as I mentioned before, when they are very deep. We therefore adopt a technique of batch normalization and gradient clipping to maintain the gradient of all layers in an appropriate range. Deep network also face the problem of the gradient degradation, that the accuracy drops when the number of layers is increased. To tackle this problem, we apply the residual structure, which is make our network very powerful, especially in the low signal-to-noise ratio. All 3 parameters in the model change dynamically as the algorithm finds the best solution achieved by the backpropagation learning algorithm, as I mentioned before. The model architecture, for example, the layer specification and their arrangement is selected through the procedure of hyperparameter optimization. We have tested efficiency of training and accuracy of prediction using different filter size, from 10 to 500 500 pixels and a model depth from 8 to 72 layers. The chosen architecture and parameter reaches an optimized balance and efficiency and the most accuracy. So you can see the hyperparameter tuning here, which make our convolutional neural network very powerful and effective. We also need to choose the optimization method. In this work, the mean square error is used as a loss function and in the regression problem, as well as Adam optimizer to optimize the loss function. What is Adam optimizer? Adam is an extension of stochastic gradient descent, which is utilize the first order gradient based optimization of a stochastic objective function to adjust the learning rate. This optimizer takes advantages of two SGD based optimizer. First, the adaptive gradient algorithm like AutoGrad, and the second root mean square propagation. And this is for non-stationary setting. And Adam is well known in the deep learning community due to its fast converge to optimize a result compared with other optimization function. And also during the training process, we applied the step learning rate. This is one of our innovative way to tackle the problem of the to increase the accuracy and being so fast. Here you can see the step learning rate, which the learning rate is reduced by order of 0.1, and we set the initial learning rate as 0.0024 for start, and after the 75 epoch it will change, and you can see the changing learning rate here. And also here we have we compared the optimizer for a regression task. As I mentioned, we originally developed FNet for redshift estimation, but as the scale and richness of a spectroscopic survey like SDSS increased, it became clear that the broader and more flexible solution was needed. And the accurate classification of a spectra is a critical step in large-scale astronomical analysis, and traditional models often rely on handcrafted features and explicit line detection, which can miss subtle spectral pattern, especially in noisy and ambiguous data. So we saw an opportunity to adapt FNet into a fully data-driven classifier that could learn directly from the raw spectra and generalize across diverse object type without relying on manually designed rules. So,
Fatame, sorry, could you please little bit try to summarize, because we are late in time?
Yes, okay, sure. So let's now take a look how we transform the original FNet model into the spectral classification. Okay. How can I be? Okay, first we replace the original single output neuron with the softmax layer to that outputs class probability, and now, instead of estimating redshift, the network assigns likelihood for the spectra being a galaxy or quasar or BAL quasar. And another, we changed the loss function from the mean square error to cross entropy. And also another change, we expand the data set, because for first project we just focus on the quasar, and now we have the vast data set like stars, quasars, galaxy, and BAL quasars. And here we can see the changes, and also we again mentioned the Adam W we have used for classifier. And as I mentioned before, we faced with the imbalance in data, and you can imagine that highly imbalanced data present a significant challenge, as most networks tend to prioritize the majority classes, and here the majority is allocated to quasars and stars. So our network maybe will be biased to this type of data. And as you can see, the galaxy completeness was 86.9%, and BAL quasar completeness was 78.8%, and star completeness was 98.8%. And the quasar completeness was 98.3%. As anticipated, a training network with this imbalanced sample prioritize quasar and stars while neglecting BAL quasar and galaxies. We attempt oversampling the minority classes and using weighted cross entropy to address the imbalance, but these methods didn't significantly improve the result. Furthermore, we can see the number of minority class spectra is approximately 30,000 for each class. Okay, so in our sample is sufficient for establish a confident training set to mitigate the data imbalance.
Could you please try to summarize within 2-3 minutes? We are late in time, please.
3 minutes, okay. Okay, you can see the result here. Okay, we have another problem for BAL quasar. I will escape. It was really important. You can read in the paper, and this is the result. And you can see for the completeness for galaxies 99%, for quasar 98.5, for BALs 99%, and for star 98.8, and which shows the power of the FNet here. And also our you can see our result for redshift estimation here. And okay, and okay, the novelty of the FNet 2 is it's the self-learning architecture. I mean, we didn't say anything. We didn't how can I say explain any prominent emission or absorption line for the network, but let the network to learn it by itself, and learns local and global pattern directly from the data, and not templates or a predefined feature. So with using the different size of kernels, and with a ResNet block and the 24 layers that I have explained it before. And also, it's really powerful to recognize the BAL quasars, and with 99% completeness, but compared to QuasarNet, which has the 78.8% of accuracy. And Yes, another novelty and achievement is we test our network on the low signal to noise data set, and we had very good completeness rate for Quasar, for 45%, for BAL 72%, and for STAR 62%, and also. Uh, yeah, and and FNet is a really high computational efficiency, and it's really fast. We use the NVIDIA V100 for training and testing our neural network, and it takes just 40 milliseconds per spectrum. And also because one of the most effective factors is using the ADAM-W for faster and more stable training than compared to ADAM or SGD. And also the training time, it takes 19 minutes per epoch on 639,000 spectra. And okay, you can see, and for details, you can see these two articles, and the data will be accessed in the prepared data can be found in Kaggle, and also we uploaded our code on GitHub. Thank you for your attention.
Thank you very much. Thank you very much. Can you hear us, Fatima? Yes, thanks. It was very nice presentation.
Thank you.
I don't think we have a question, but online people, do you have a question? Doesn't seem the case. Okay, so thank you for all the morning presenters. So we'll be connected in the afternoon, no? At 2 o'clock, Italian time, we will connect at 2 Italian time. So thank you very much and see you later. Close the connection. Close.